Hello, this is Mark Werwath. I want to go through the Nuvention Energy offering that we deliver every year to both grad students and undergrad students. And I want to review this from the perspective of what role research faculty can play, and specifically Northwestern University Technology can play in terms of seeding this course for projects that students can build business models around and develop business pitches and evaluate them from a commercialization perspective. Before I start, let me just review what the course is about. It's been sponsored by ISIN, the Institute for Sustainability and Energy, here on campus for the last 10 or more years. We basically are supporting their mission by educating students on clean energy and clean tech as applied to commercial applications. Students are encouraged, in fact, they're required to form teams and to develop their business models in teams using cross-functional teams as a basis for understanding both the technology, the application, and the business use across a variety of markets. And in fact, their job is to evaluate those markets to find the most feasible markets, the most profitable markets, as well as the most profitable applications and business model approaches. What we leverage in this class is, first of all, a vertical alignment. So we do not allow students to work outside of the clean tech space. We'll define that in a moment, but we do have other verticals for the Nuvention model. We've actually had a Nuvention Medical, a Nuvention Web, a Nuvention Analytics, Nuvention Transportation, and I've taught several of these over the years. So the Nuvention model is one that does expand across other verticals, but I am specifically talking about the Nuvention model here in this video, because I want to appeal to those researchers that work in this clean tech space so that we can apply their technology to this course, right? We bring in experts from the field who act as advisors to the student teams. We have multidisciplinary teams, as I mentioned before, creating innovative business models in support of clean technology solutions. We leverage lean startup methodology. Bill Aulette in particular, who has authored a fantastic textbook on this. We leverage often technology from Northwestern. So students can bring their own technology, or they can leverage technology from NU, whether it's from INVO directly or whether it's coming from the research faculty. We've done it both ways and it seems to work pretty well. We also bring in industry leaders as guest speakers. And as guest speakers, these students are able to see a variety of different applications, different challenges in the industry, different sets of needs, and different applications that frankly will hopefully stretch their mind into thinking in different directions in terms of how technology can be applied to solve the clean tech problem. The learning objectives for the course is, first of all, we want students to develop the ability to create a business model and to conduct specific customer discovery interviews. So we're going to require anywhere from 30 to 60 interviews throughout the quarter. Some students can actually go as high as 100. We want a cadence of maybe 5 to 10 interviews per week to be pretty much the norm, whether they're inside the class or outside the class. Once they graduate from the course, frankly, if you're going to start a business, it would make sense to continue that cadence. We want them to have the ability to pitch their business in under 10 minutes in a very compelling way to almost any type of audience, hopefully in particular a non-technical audience, because frankly, a lot of these technical students with in the PhD programs or science backgrounds tend to overcomplicate. And in many cases, our job is to help them simplify the message and simplify the delivery. We want them to be able to apply lean startup techniques to the startup endeavor, to the project itself, as well as establish an understanding of clean tech solutions and industry challenges to address global climate change. So what we want them to be able to do is to assess the impact of these technologies on greenhouse gas in particular. So how do we define clean energy? Really those solutions which have a positive impact on greenhouse gas that focus on the energy, water, food nexus. So why that definition? Well, frankly, it's because it's the same definition as the Clean Energy Trust, and it does lend itself to a variety of projects, both everything from solar and wind to clean water projects, et cetera. We want those solutions to have a positive life cycle analysis, ones that are obviously more self-sustaining than whatever is in the current marketplace. Typical student census looks like this. We have about 30 or so students, mostly spread across 2 different sections, ISIN and Entrep. We're open to all NU schools. So you're going to find business students, engineering students, students that are both undergrads and grads from various NU schools, including the law school. We usually have 7 or 8 teams of 4 to 5 students. We have a steering committee of faculty that help define what we're going to deliver that quarter. We have subject matter experts that are basically people that come in as guest speakers or faculty members. And then we also have an advisory board, and you'll see a list of what that AB looks like. But again, those are outside industry experts and people that basically provide a bridge or a link between the classroom experience and the real world. Typical census looks like this in terms of, last year's class had 27 students, good mix from grad McCormick to undergrad to Kellogg to law school, et cetera. So you can see a good blend there. You can see our advisory board members here from a variety of industries, including Lanzatech, which is a biofuels industry, Eric Burkertz, who's the CEO of Clean Energy Trust, and Tim Stoika, the chair, who's the CEO of Agentis Energy. We have a variety of guest speakers. They do somewhat overlap with our AB, but often they don't. You can see last year we leveraged Professor Sosina Haley, who brought in her clean energy technology to the class, and we wrapped a team around that, and you'll see some of the results later in this presentation. We do look at the regulatory and policy aspects because we want students to understand, especially when it comes to electric energy and the grid, because that does become a focal point for this course. Our fundamental belief is that, the solution to clean energy problems and to the greenhouse gas problem is to basically green the grid, right? So make it, in essence, as carbon-free as possible. So decarbonize the grid and then convert everything over to electrification. So that's the transportation as well as virtually every other aspect of energy consumption. If it can be electrified, and then if the grid itself is green, we are much, much closer to reducing greenhouse gas in the atmosphere. So these guest speakers represented a good variety of different disciplines as well as different industries that all are focused on clean energy in one form or another. The faculty involvement. So what can we hope for from the audience here, right? Faculty with relevant intellectual property that can be applied to clean tech applications are invited to share those inventions, those technologies with the class. We can schedule 15 minutes as we did with Professor Haley, and we can do that very early on, week 1 or week 2 of the class, so that interested students may form a team to develop business model canvas and a pitch deck for use by the faculty as their final project deliverable. So this is what we're inviting you to do. It's all governed, of course, by INVO processes and INVO procedures. We've worked with them over the years to develop a very robust approach so that when a student team champions a technology from the shelf, they can earn their right to get a license from INVO. So that whole process has been well laid out. It's not necessarily a simple or easy process, but it generally starts once the quarter is over. And once the business model and business case has been pitched to INVO, they can assess whether or not they want to continue with this as a potential licensee situation, or they want to waive that. So students who have their own technology will eventually go to INVO for waivers in the event that they want to go into the wild and commercialize their own projects. These are the intellectual kind of foundations of the course. Bill Aulett again, discipline entrepreneurship, variety of case studies from Harvard Business School. We might do upwards of 10 different case studies throughout the quarter. And of course, Gretchen Baki's book, which really talks about the grid, the history, the current state of the grid, the problems, the opportunities, as well as the potential future, which clearly she lays out the future of the grid being distributed generation. And I'll get into what that means in a moment. What we do teach is some fundamental basic concepts here. The first one is that energy supply and demand must be balanced at all times, 24/7 on the grid, 365 days a year. That becomes somewhat of a challenge when demand is volatile, and it also becomes a challenge when prices are not static. It's also quite challenging because there's very little energy storage on the grid as we know it, right? So Storage is kind of an elusive concept that we've been pursuing. Yes, there's little pockets of storage here and there, as you can see in this photograph, but that is very rare. It's kind of few and far between compared to the net amount of energy flowing through those wires. So what you see in the lower right is a graph of how energy prices fluctuate throughout the day. Consumers have little access to these real-time prices in a meaningful way to adjust their behaviors accordingly. As a result, there's a lot of elements that are in place, such as smart meters, but there's really no compelling user interface or mechanism to adjust people's behaviors to match the price at hand. What this fundamentally creates, though, in my mind, from a business perspective, is the obvious arbitrage opportunity. So if you can buy energy low, and this is calibrated in euros per megawatt hour. So if you're looking at, let's say, a low of 40 euros here at something like maybe 4 o'clock in the morning, and then by 9 a.m., it's peaking at something like 60. That delta between 40 and 60 becomes an opportunity for buying low. So invest by buying energy and storing it in the early morning hours, and then selling it back to the grid by 9 in the morning. You have that opportunity again in the afternoon to, again, buy low, perhaps at 48 euros per megawatt hour, and then peaking at 64. So in our market, we calibrated in more or less pennies per kilowatt hour, and our market can fluctuate from 1 or 2 cents, which is what I checked this morning, upwards of maybe 20 cents per kilowatt hour at peak demand. So that's a 10x or maybe even 15 or 20x span from peak, from trough to peak. So I talked about distributed generation. This is what the grid looks like today on the left-hand side, which is mostly a push model from a centralized generation capability. So the plant, the power plant that generates the electricity is pushing electricity through the grid to these various load centers, whether it's commercial, residential, retail, variety of different applications, as well as industrial. You've got all these different sinks, right, in essence, and you have one single source. But that's not really the way we're going, right? The way we're going is having hundreds or thousands of sources of electricity. Every house could be generating its own electricity through solar panels, through wind. So this green on the right-hand side basically shows the grid of the future, right, which resembles more of a computerized network. So not too much different from what happened in the late 90s when standalone computers started to become networked with each other. Those computers then were able to access the internet, and the internet was allowing, in essence, communications and information to flow in a peer-to-peer fashion. This is effectively where energy is going. So we will have the Internet of Energy in the future, where energy can be transferred across its own grid, and you have producers and consumers accessing that grid. Often the same entity can be both a producer and a consumer. So you'll have less of a need for centralized generation. You'll have more distributed generation, and you'll hopefully have a smart 21st century grid that can manage this flow of energy from everywhere to everywhere, which is not today's model. Okay, so we need to ruggedize that grid. We need to modernize that grid. We need to make it more intelligent. And I believe this is the type of talk that we're seeing and hearing in Washington as an investment opportunity that could be measured in the tens or maybe hundreds of billions of dollars. So once we do that, we have an opportunity then to decarbonize the grid. And then we also have the opportunity to electrify virtually the rest of society, mostly the transportation sector. One example, buses, right? City buses alone. We have fewer than 1,000 electrified buses in the US. China has 400,000 electrified buses. Another opportunity here that we saw from one of our teams was a team called Blip. What they decided to do was monetize this arbitrage opportunity that I mentioned earlier. So this little box here is an energy storage box. So it can purchase low-cost energy at 3 a.m. and then deliver that to the air conditioner at 9 a.m. When you want to be cool at 9 a.m., you're using stored energy as opposed to energy off the grid. So in essence, you're buying low, selling it to yourself when it's more expensive, and cutting yourself off from the expensive energy, trying to tap into only the inexpensive energy. So this is what Blip That's what Blip's business model is, providing this kind of opportunity to the consumer to save on their energy costs, right? I myself am a ComEd real-time price user, and I can save easily 20 or 30% by shifting my load from daytime to nighttime. I run my dishes in the middle of the night. I charge my car in the middle of the night. This was the team that pulled that together. They did an amazing job. In fact, they're still out there in the wild. We've had several MBAs here and a couple of PhDs. The MBAs have a very interesting and varied background, and so do the PhDs, ironically. So I think it's a pretty robust team. They are still working at it, and they've already got some grants, some non-dilutive capital. And I know they've been going through the Farley Center for managing some of those venture well grants. One of the analyses they did was market analysis. You can see they're comparing different types of homeowners versus renters on the y-axis, price sensitivity on the x-axis, and looking at this from a kind of market segmentation perspective, trying to understand those characteristics, what some of those needs and desires are, and whether or not their solution will fit into those various segments. They understand that, of course, through the various interviews that they do, again, upwards of 50 or 60 before the end of the quarter. You can see these interviews, basically how many, they're focused on renters now, right? They wanted to understand the value proposition in the mind of the renters, whether they're looking for payback, whether they're looking for cost, whether they're looking at aesthetics or resiliency, because there's also a potential resiliency play. Whenever you have a battery sitting in your home, it can act as a backup in case of a power outage. So again, some verbatims, trying to understand exactly what that market is looking for through the interview process. A second team that I wanted to showcase, the one from Sosina Haley's laboratory, is the nitricity team. At its core, the nitricity technology takes electricity, air, and water and creates through the cell, in essence, a fixed nitrogen ammonia-based fertilizer for use in agricultural applications. So the beauty of this situation here is if you have cheap electricity, and it turns out that the farm does have cheap electricity. In many cases, if you have a windmill on that farm, you may have excess electricity that is not being used by the grid. That can be then deployed with combining with the air, water, and the cell itself to create this ammonia. So the way to think of this cell, at least the way I think of it, I hope the professor agrees, I see this as kind of a fuel cell working in reverse to what we would normally think of. So fuel cells, we often think of generating energy, right, from an input as opposed to the other way around where we're actually using electricity to create an output. So this, in essence, nitricity cell will be potentially a distributed storage capability for excess electric energy, right? So if you have excess energy here, you can store it in the ammonia over here. Now, this is not exactly mainstream thought. Mainstream thought is to use hydrogen. So we'll talk about that later, but hydrogen is one of the other options for comparing the various energy storage capabilities for the grid. So this is all built on the presupposition that there's going to be increased demand for nitrogen. And of course, as a fertilizer, you can see from this graph how many people we can support on the planet in the absence of this synthetic fertilizer, and what we're going to need in the future as we grow from 6 to 7, pretty soon 8, 9, 10 billion people on the planet. They all need to be fed every day. And this is going to be one way to at least enable that. So there's going to be a growing need, an ever-growing need for nitrogen, as well as understanding the size of the market in dollars, the cumulative annual growth rate, as well as the quantity of nitrogen that's going to be needed in the marketplace long term. So this is part of the analysis that every team has to do when they're going through our course. The other thing they have to do is also look at the competitive analysis. Here you're looking at 5 different competitors, the main 5 in the US. The ones are shown here, what market share they have, how much they're actually generating in terms of dollars as well as volume. Another view of that is shown here in terms of an even more granular view of who's playing what role in this global fertilizer market. And these are the top players as of 2016. I mentioned that you can use hydrogen as another energy storage capability. This basically compares hydrogen to ammonia as a potential energy storage option. remember too that if we have a highly centralized solution today for creating ammonia, otherwise known as Haber-Bosch, right? That centralized approach will require a lot of energy to distribute. So transportation energy, transportation costs have to be factored in whenever you're comparing, say, Haber-Bosch to this approach here, the nitricity approach. So you can see how they're looking at the hydrogen versus ammonia trade-off. Here's a trade-off that they were looking at this approach versus Haber-Bosch, because in theory, this could replace Haber-Bosch on a distributed basis. So instead of having natural gas as an input hydrogen source, they're using water. Instead of having 500 degrees C reaction temperatures, you're seeing 250. So lower temperature, lower pressure, less energy consumed, and a more reasonable hydrogen source that doesn't add to our fossil fuel problem in the US. So all the advantages, in my mind at least, give Nutricity an advantage over Haber-Bosch. Again, this is a fuel cell in reverse. That's at least the way I like to look at it. There's a lot of advantages that went beyond this. They actually calculated how much greenhouse gas would be saved across the planet if all the ammonia was generated from nitricity rather than Haber-Bosch. They were able to look at a lot of the techno-economics and unit economics. So bottom line, this team did a very thorough job. In fact, they were pitching in front of ComEd just the other day with a very thorough analysis. So this team continues to work on the business model development. I'd like to think that they got their acceleration from the course in Nuvention Energy. Another example or set of examples here from 2019, we looked at microgrids, we looked at microgrid applications in hospitals, we looked at shifting demand for hotels and other markets. We've looked at thermoelectric materials from power threads. This came straight out of the laboratory. This was an INVO licensable technology. And ironically, this team looked at it for combat situations. We looked at BioBoost for various DNA strains that were enhancing client strains for fermenting chemicals. So we've had a lot of interesting projects go through Nuvention Energy, and many of them are out in the wild trying to compete in the world and in the marketplace. My last slide here basically shows some of the successes we've had. The Rice Business Plan competition is one of the most prestigious in the energy space every year. Student teams are awarded anywhere from $50,000 to maybe $250,000 of non-dilutive capital. We've had great success. New Mixed Materials last year, which was removing heavy metals from aqueous solutions. A team out of McCormick Tech, right, leveraging Northwestern technology, was the 2018 Energy Prize winner. They later went on to Argonne Labs to become part of their clean energy accelerator they have over there. We were also awarded by Hazel Technologies. Hazel was looking at fruit and the ripening of fruit and how to delay that by using various ethylene absorbing materials. So they are actually doing quite well. They're actually in production now, and they've got some great customers lined up. The 2013 champion, Synode, which was a lithium-ion battery play, basically looking at the anode and using graphene in the anode to enhance the performance of the battery. Very successful team, recent exit. In fact, Samir Mayakar, who's pictured right here, is now on the mayor's staff for the city of Chicago. Brightseed was a Nuvention medical team, and of course, Numat, which goes back all the way to 2012, now almost 8 years, was looking at the storage of gas, natural gas, in a compressed CNG type format. So we've had some great exposure, great experience, great results out in the market. I would like to do more. I think we are capable of doing more. So my challenge to I guess the faculty, the AB, and to some extent to the people watching here is how can we expand that going forward? How can we have better success for Nuvention Energy and commercializing Northwestern technologies and accelerating the clean energy challenge as we go forward? That's what I guess I need your help with. So thank you for your time.